Yes. Thank you, Renee. So thank you very much for the invitation. Thank you for for asking me to talk about this. I actually didn't know about this nice online colloquium series connected to this COMETA. Is very nice and very nice thing. So as far as I understood, so first of all, of course, you can somehow shout. I don't know if there is a way for you to ask questions if you want. Otherwise, there will be questions, I guess, at the end. I understood from Renee that the people joining might be very diverse in the topics, right, that you work on. And so from that point of view, this is, of course, scattering amplitudes can be a very technical topic, but I will try to somehow give you an idea of where this connection through scattering amplitudes from collider physics to geometry comes from. It will have to be slightly technical at some point, but hopefully nothing that goes beyond what we learn in first year and second year of undergraduate mathematics. So hopefully everyone can follow. Yeah, so the title is Scattering Amplitudes from Collider Physics to Geometry. So I will start briefly talking about collider physics, which is what I mainly do, or at least motivates a lot of my work. Colliders, and in particular the LHC, are incredible machines, right? And one of the questions that we can ask ourselves, and people have been asking ourselves, is why and whether it makes sense to keep on investing in colliders. And I think it's important, right, to ask ourselves these questions. And I think that the LHC itself, as the last and the most powerful collider that we have, as demonstrated, indeed these machines are incredibly powerful, and their power also lies mainly in their flexibility. In fact, I mean, the LHC has shown this flexibility already when it has transformed itself, in a sense, from a discovery machine, which is what it was supposed to be at the beginning, when people expected to discover not only the Higgs boson, but many other supersymmetric particles that should have completed somehow or extended the standard model of particle physics for various reasons. Into a precision machine, because these particles have not been observed, at least till now. And instead, the LHC has been able to, despite being, as we will see in a moment, a pretty complicated hadronic machine, to transform itself, as I said, in a precision machine, for being able to scrutinize the standard model to very high precision. And this is one of the examples of the plots that we typically see beautifully produced by the experiments. For example, this one by Atlas, where we see how many observables and how many different final states have been measured to very high precision. Now, of course, a lot of the precision and physics program in general at the LHC has been revolving around the Higgs boson. And of course, this makes sense because the Higgs boson was the last particle to be discovered. It was also, in some sense, the coronation of the standard model of particle physics itself. It was the last missing piece, the last piece of matter that we had not observed. But it's not only, of course, the last missing piece from that point of view, it's also somehow tied together to many of the fundamental questions that we still cannot answer, inside the standard model at least, about fundamental aspects of the universe and of the reality that we see around us. Starting from the origin of the universe, also its thermal history in a sense, the problem of naturalness, its uniqueness, the uniqueness of the Higgs field, whether there is one or there are many, the origin of flavor physics, of flavor in general, the origin of masses, of course, and so on and so forth. This was like nicely summarized by Snowmass 2 years ago for the 10 years of the Higgs discovery. So of course, this particle is extremely important. It's connected to so many profound questions. And what is important now is that, of course, colliders at this point, and in particular the LHC, are the only machines that we have available that can open a window for us in studying this part of this type of questions. And the way the LHC has done it, right, is really allowing us for the first time to see the part of the Lagrangian of the standard model that tells us how the Higgs boson interacts with other particles, because all these questions about the origin of masses, the origin of dynamical questions about the standard model, if you want, from spontaneous symmetry breaking to the CP problem, for example, are connected indeed to how the Higgs boson interacts with all the other particles. And this is the part of the Lagrangian that we see here in this red circle. And in fact, if you go and look in detail, right, at what happened in the last decade in a sense, but also in the last 2 decades or 15 years since the LHC has been running, is the first part that we have seen really of this Lagrangian is the so-called gauge sector is practically synthesized in this part of the Lagrangian here, which tells us how the Higgs field, this phi field, interacts with the gauge bosons. And this is how the Higgs was observed, right, in 2012, in its decays to Z bosons and photons. Is also the part of the Lagrangian that we understand best because it's also its form, somehow the form of this covariant derivative is really dictated by gauge invariance. When we go beyond that, though, the other parts of the Lagrangian, we know much less about them. For example, for what concerns the coupling of the Higgs boson to fermions, for example, to quarks, of course, and to leptons, we have a model, which is the Yukawa model, right? So we have like modeled somehow this interaction in the simplest way that we could do that to make it consistent with all the properties that we believe that this Lagrangian is supposed to satisfy, for example, gauge invariance. This is the simplest way we can do that. But of course, no one tells us that this type of interactions should be exactly in this form. And the only way we can go and scrutinize and see if this is true is actually go and observing and measuring whether the Higgs couples to the different fermions according to their masses practically, which is what this equation tells us. And interestingly, the LHC through run 2 already, and now with run 3 and the high luminosity LHC, it has the potential to really go and measure with very high precision all the couplings to the third family fermions, which are tops, bottoms, and taus, and also to start seeing glimpses of couplings to the second family. And also, of course, it will be very interesting also for physicists, for phenomenologists, for experimentalists, to think about new methods to use the data produced by the LHC to go beyond what we believe is possible today, right, from this point of view, because it's also one of the most interesting things, finding new ways to exploit the data to get more information about what, for example, these couplings, which are very difficult to observe. And finally, there is the part that is probably the most mysterious, right, about this Lagrangian, which is how the Higgs boson couples in a sense to itself. So it's the Higgs potential, which is the one that determines the spontaneous symmetry breaking mechanism. And also in this case, right, if you think about it, we have a model about spontaneous symmetry breaking mechanism, which is very similar to the effective model that we have to understand superconductivity. But of course, in superconductivity, we have a dynamical explanation. We have Cooper pairs. We know exactly what happens inside the superconductor. From the point of view of spontaneous symmetry breaking in the Higgs field, there is no dynamical explanation at the moment. We just have this toy model, this Higgs potential, the famous Mexican hat. But again, also here, actually, there is no reason to believe that this should be really the potential. In a sense, still in some slide from Gavin Salam, what we actually have seen now here are small oscillations close to a minimum of this potential, right? Which would be, for example, the blue one, but could be also the red one or any other potential that has a similar minimum here. And what we would like to do is actually do more and more precise measurements that allow us to actually constrain, if you want, the full Taylor expansion of this potential close to this minimum. And so there is hope, right, that accumulating all the data from the LHC, we will be able in the coming years to see the shape of this potential better and better, and so to make statements about, if you want, something that is very fundamental, which has to do with really fundamental property of the universe, how spontaneous symmetry breaking mechanism happen and how masses are generated. Now, how do we probe all these sectors? I told you about these 3 sectors, right? The gauge sector, the Yukawa sector, and self-coupling, somehow the potential of the Higgs. Well, we do that studying complicated finite states at the LHC, fundamentally. So these are some examples. In order to probe the gauge sector, we usually want to produce gauge bosons. So these are examples of processes where we produce 2 or 3 gauge bosons as finite states. And you see some of these processes measured at the LHC with different precision, depending on the complexity of the finite state. Similarly, if we want to probe the Yukawa sector, you also see we have to produce like different massive particles in the finite state, for example, top quarks in a Higgs or bottom quarks in a Higgs, and so on and so forth, and go and measure, right, these cross-sections or different observables related to these cross-sections. Similarly, for the self-interaction, well, here things actually become extremely complicated, because if you want to see the self-interaction directly, the only way we know at the moment is to go and measure the production of 2 Higgs bosons. But the cross-section for two Higgs bosons is extremely tiny. It's 1,000 times smaller than the cross-section for a single Higgs boson. In fact, not even the LHC with a full high luminosity run will be able to really see this with more than 4 sigma, so really to make an observation. But what is interesting is that there are new ways, right, also indirect ways, and people again are thinking about different observables where one can go and see maybe indirectly this triple Higgs coupling, again through precision studies. And this is an example, right, in the production of a vector boson and a Higgs associated production where you have also a coupling, a triple coupling of the Higgs. So this can become a very fascinating and very interesting and challenging effort from phenomenology experimentalists, as I said, in order to try to find new observables where we can do things that are at the moment unthinkable. And this has already happened, right, many times. On top of this, of course, there is a lot of Higgs, right, in the LHC program, and people talk a lot about Higgs. I also talked a lot about Higgs to motivate what we do. But I also want to say something more. There is not only the Higgs, right? Because when we go and do these experiments and colliders, and of course theory calculations to check if what we measured matches what our theory predicts, what we actually do is actually in general testing quantum mechanics and special relativity, if you want, which is the formalism that we use to describe particle collisions at very high energy, which together make quantum field theory, at the highest possible energies. This is an example, right, where many jets of particles are produced, and this is a Feynman diagram of how we would, for example, try to model processes of this type, production, for example, of 3 jets. And we have to think about this fact, right, that when we go and do these calculations to very high precision and do these experiments also to very high precision at the LHC or at other colliders, we go and really probe quantum mechanics at the highest energies and at the highest precisions. And so, in a sense, if you allow me to shoot in the dark a little bit and to be maybe to dream a little bit and maybe to overstate something, so please take what I'm saying with a grain of salt. In a sense, colliders allow us indeed to test and to stress test the formalism of quantum field theory. And now we know that in the universe, right, there is much more than the matter that we can describe with the standard model, which is based on quantum field theory. And we know that a lot of the unanswered questions about the universe, the ones on which we really somehow don't even know where to start from, they are somehow tightly connected to a part of the if you want, the interactions, which is gravity, which is the part that we understand the least, or maybe we don't understand at all, depending on who you ask. Quantum gravity, in a sense, will very probably require an entirely different point of view. In this sense, one could even dream that stress testing the limitations of quantum field theory might suggest also how to go beyond this formalism. Now, of course, as I said, I'm shooting in the dark a little bit here, but it is important because when you don't know what to do and you have a formalism that is so powerful as the one of quantum field theory, but so limited to, if you want, the 5% of the matter that we observe, we need to find a way to somehow go and really at the boundaries of this 5%. And this could be one possible way to do it directly. So this is all to say that of course, it's true that we don't really expect to discover new particles necessarily after the discovery of the Higgs boson. It might be the first time in history where we don't expect discoveries of new particles necessarily in front of us. But we have, first of all, a lot of new interactions to discover, and these are discoveries which are really the way how the Higgs interacts with particles around us, and all these possible questions that are connected to these interactions, which are fundamental questions about the origin and the evolution of the universe and the matter around us. And also we have the opportunity to scrutinize quantum field theory to the highest precision and to the highest energies to try to test these limitations. And I think these are very important things to remember. So this is my very long motivation, and also to tell you that, of course, in order to do all of this, we need to be able to understand complicated processes like the ones that I've tried to sketch and to go through in the first part of this talk. So usually we want to produce many particles in the final state, massive particles like tops, Higgs, vector bosons, and these calculations are extremely complicated. And this is what we're going to talk about, in a sense, in this talk, and what people like me, of course, and René and many other people are dealing with most of their time. And of course, one more thing, important thing, is that we want to do this at high precision. LHC has already reached, as I tried to show you with this plot that now is half hidden, percent level precision with some of these observables, and we only have collected 5% of the data. So a lot of more luminosity will be collected starting from next year. And we really have the opportunity to shrink the precision on these error bars experimentally in most of these observables. And so we will have to somehow, if we want to pursue this program that I just described, and stress test standard model, the standard model and quantum field theory, this gives us a strong motivation to understand these processes theoretically at the same precision. Okay, and so how do we get there? So how do we get to this percent precision for such complicated processes, for such complicated final states like the one that I showed, like the ones that I showed here? So indeed, we have a Lagrangian, which looks very simple and very beautiful. You can put it on a coffee mug, as we know, or on a t-shirt. And then we have distributions that we produce. And going from one to the other and comparing these distributions to experiment is actually extremely complicated. It's a very long way, as I tried to say here. The reason, going back to the picture that I already used, is one of the main reasons is QCD, the theory of strong interactions. The theory of strong interactions indeed introduces an extremely complex dynamics in these processes, not only because quantum field theory is complicated in general, but also because the strong interaction suffers, or if you want, enjoys, depending on the point of view, of asymptotic freedom. Namely, the interaction becomes extremely strong at low energy, and in particular non-perturbative, and it becomes low, so small, at high energies, which is where asymptotic freedom comes from. Which means also that when we study collisions of particles, there is always a bunch of collisions energies, and there is a part of the collisions at some point particles lose energies and become very low energetic, and there physics becomes inherently non-perturbative, and the description of these processes becomes extremely complicated. So one cannot just use perturbation here. Indeed, when we try to think about these processes, we have usually, as theorists, of course, a very simple picture, which is the one of two protons, which are these two P's here that collide from left and right, made of 3 quarks each. Something happens in between, and some hard particles, some very energetic particles, for example, a Higgs boson is produced, it then decays to something, and maybe a jet of particles is produced on the other side. And at the same time, maybe some other soft or collinear particles are emitted during this production. This is the complexity, right, that I was talking about before, in a bit or more schematic way than the nice red plot that I showed at the beginning. Still, this picture is complicated, right? And so what we actually do is that we use what is called the factorization picture in order to try to make sense of this and to split it into pieces that we are able either to calculate or to infer from experiment or from some other calculation. Factorization is one of the central things, right, in quantum field theory, but in physics in general, because it's something that tells us that the physics that happens, say, at very high energies cannot really influence the physics that happens at very low energy, or if you want, very big distances and very small distances don't really interact with each other. If you want to do experiments with atoms on Earth, we don't really care about what happens on the moon or what happens on the sun. Now, quantum field theory as a formalism has given us a way to actually make these statements very precise. And this is what factorization theorems are. They are exactly a way to make very precise statements about how high energy and low energy factorizes and splits, and what is the error, the mistake that we make when we make this assumption. In this type of picture, the type of factorization that we think about is the following. So we have our non-perturbative objects, which are the protons, which are low energetic bound states of quarks, which collide at very high energy. So there is a low energy physics inside the protons, which is in these Spartan distribution functions F, which we cannot say anything about. We need to measure from experiments. Then there is a very high energetic cross-section that we can compute in perturbative physics and happens in this blob, and this is the partonic cross-section or the hard cross-section, because hard is what it means to be very energetic. And this we can compute perturbatively because the coupling becomes small, thanks to asymptotic freedom. And then we have corrections, right? And these corrections can become bigger and smaller depending on the process. And this is actually very complicated. I'm not going to go into this because this would take us too far. But the point is that for processes, for some processes, one can make this statement very precise and tell exactly how big these corrections are. So we're going to focus on this, right? So we are going to assume that these partial distribution functions have been measured with very high precision, and that if you want, this factorization is under control to the right precision that we want, which is the case, right, for many processes. And so we're going to ask the question on how we go and look inside this blob here and compute this hard cross-section to the percent level precision. So what is a cross-section, right? So if you think about even going back to quantum mechanics, which is what we all understand, the way we compute cross-sections, I mean, we have beams of particles that maybe scatter on a target. This is a drawing taken from a undergraduate book. The way we compute the cross-section, so the probability of finding, if you want, our scattered wave here in the detector is actually through a scattering amplitude, right? So we have an object, which is a scattering amplitude, which we can compute. Here is written, in particular, expanded in partial waves. And then we take the scattering amplitude, we square it, and we integrate it over phase space, and we get our cross-section. Now, there is a very important thing to notice here, that the scattering amplitude already in quantum mechanics, which is what makes it quantum somehow, is complex, right? It has a phase here, and these phase shifts here, this delta L or whatever they're called, they're actually what determines, if you want, the whole physics in the scattering process, and is what in quantum mechanics you spend all your time computing when you do scattering. You compute these phase shifts delta. And it's also the reason why when you compute a cross-section, you have to take a modulus in a sense of an absolute value, in a sense of a complex number, and you have to square it. And in taking this modulus, you can generate different interference patterns, which are what really differentiates quantum mechanics from classical physics. Now, when we go to quantum field theory, things work exactly in the same way, right? So we have a cross-section, for example, for producing two gluons in two quarks, or scattering a quark and an antiquark. And we have also a scattering amplitude here that is also a complex function. And this complex function has to be squared, right? And then has to be integrated over the phase space of the two gluons to produce a cross-section. Or if we put some constraints on this phase space, we can produce some more differential distributions. Now, if we assume that the energy is high enough, and we think just about QCD for now, which is the biggest part of the interaction, is also the one that suffers of asymptotic freedom. And so from this point of view is the one where this discussion applies the most. If the coupling is small, as it is the case, for example, at energies around 100 GeV, which are the typical energies of scattering processes at colliders, this coupling is small, so 0.1, the strong coupling. And so what we can do is we can take this quantity, the scattering amplitude, and we can actually try to compute it as a perturbative series in the coupling. This is what we do. So we expand leading order, next to leading order, next to leading order. This is what this LO and LO and next to leading order stand for in the coupling alpha strong. Of course, just from a rule of thumb calculation, if the coupling is 0.1, you would expect that this quantity here is 0.01, which is the 1% that we need, right? So we would expect we need to go at least to this order to get percent level precision. We will see that sometimes this is not even enough. Now, how do we compute these amplitudes? Where in quantum mechanics, we would use a Born approximation for the leading order, and then we can use different types of perturbation theory to compute complicated approximations on top of that. Also in quantum field theory, we do that, and we have the nice instrument of Feynman diagrams to visualize these different levels of approximation. So at leading order, we typically produce what are called three-level Feynman diagrams, so diagrams of this type. We notice, first of all, that in this case, the precision that one gets out of this calculation is very rough. It's just a rough estimate of the total cross-section. But what is interesting here is that independently on the complexity of these diagrams, which means how many particles you want to produce, we have actually very powerful techniques today to understand all these calculations completely in general. So these are called on-shell methods, and they allow us to do these calculations without even having to produce the relevant Feynman diagrams, which is very powerful, but is in a sense constrained to leading order. When we go to next leading order, things become a little bit more interesting, right? Because what happens is that the pattern becomes a little bit more complicated. We don't only have diagrams like the ones that we saw before at 3 level, but now with one additional emission, because with one more emission, we have one more power of alpha, which is the reason when we square this, we have one more power of alpha, which is the reason why we have to have an additional emission. But we can also get an additional power of alpha by having like loop diagrams, like these ones here. These are called virtual corrections because we have virtual particles going in the loops, and these are called real corrections. Individually, the two pieces are not well defined, exactly because of what we just saw, right? That I can have like a diagram with an external particle, and this particle can, for example, the energy can become very small, and then I don't see it in my detector. So it's actually very impossible physically to distinguish this type of diagrams for these ones. I have to consider them together, and only when I consider them together, I get, if I do things properly, something finite, well-defined, and that I can compare with the experiment. Now, all of this is very well under control now. We understand very well how to do one loop amplitudes, virtual amplitudes, how to compute these ones, it's the same as before, and how to put them together. And when we do that, we get much better precision. We see something between 10 and 30% precision on the finite cross-section, depending on the process again. So it's still not enough to go to the percent level. We have to go to 2 loops, right? At least, as I said. And in fact, if you go to 2 loops for typical processes, you get much better precision, still not really 1%, but definitely closer to 1%, again, depending on the process. And you see that the type of pattern that I just described becomes much more complicated. So you have like, of course, again, diagrams with more external particles that are called double real because you emit 2 more real particles. We have real virtual particles where you emit 1 more particle, but you have also a loop. And then you have 2 loop diagrams, right, which are double virtual objects. Now, again, since we understand very well 1 loop amplitudes, and we understand very well how to cancel the divergences patterns between these 2, right, this part of the calculation is kind of well understood. What becomes difficult, again, is actually computing these 2 loop amplitudes and then cancel all the divergences that actually come when 2 of these patterns become, for example, soft or collinear, unresolved, and this pattern becomes unresolved and so on, and then new divergences are produced, and this makes, of course, everything more complicated. Now, all of this at this order is actually very well under control. The cancellation of these divergences and how we produce finite quantities putting these 3 ingredients together. Again, I'm not going to go in detail into this. This can also be very technical, like many of the things that we are discussing today, and it would be a completely different talk. You can ask René to explain you how this works much better than I can do. But I'm going actually to focus on these amplitudes here, because these remain at 2 loops, but also higher loops, often the bottleneck in this type of calculations. Let me also try to argue with you with a plot that I stole from Massimiliano Grazzini, how important it is to do these calculations, because sometimes when we talk to people not doing physics or doing other branches of physics, they actually ask us why we want to do precision physics at this level, right? Why are we not happy to get the result that is correct, more or less at 50% precision? Well, the point is exactly that. You see, if you try to compute, this is the cross-section to produce a Higgs boson. So one of the most important things that has been studied at the LHC in these years, and you just do a leading order calculation, so just what would correspond to the 3 level. In this case, it's not really 3 level, it's 1 loop, but whatever. And you compare it to the experiment, then you actually see that there is a huge discrepancy. And so you would be observing new physics. But if you keep on including new orders, and the band is the uncertainty, right, of the calculation. So if you keep on including new orders in the expansion, for example, next to leading order QCD, next to leading order QCD, and then also more effects like electroweak theory, resonation, and more stuff, then you actually find that only when you go to n-cube below, so even 1 order higher compared to what I showed you before, then you finally get a very nice convergence of the perturbation series, and you see that indeed the result seems consistent with what the experiment measures. And now this requires very complicated calculations. As I said, I showed you two loop diagrams when talking about next to next reading order. If you want to go to a Q below, you need also three loop diagrams and things. Of course, if you start having electroweak theory, and then you have Z bosons going in the diagrams, massive, massless particles. So they can become extremely complicated. So what I want to do now is somehow tell you a little bit about these diagrams, why they are complicated, and why and how we compute them, how we think about them, and where is somehow this connection with geometry that I was trying to hint to in the title, right, of this talk. So where does it come from? One possible way, at least, to look at it. So, okay. So let's have a look at what these things look like, because for now I just only did some drawings and said some words, but maybe I don't know if all of you have seen and manipulated Feynman diagrams before, maybe not, or maybe yes, I don't know. So A for me represents now an amplitude, and what is an amplitude, a scattering amplitude, where we, as I said, we decompose it in Feynman diagrams, right? And this would be an example for a Feynman diagram where two gluons produce a gluon and a Higgs boson. Now, of course, there are a lot of information in these diagrams. For example, Santinet tells us that the gluons are gluons, polarization vectors that tell us how the gluons are polarized. There is something that tells us that inside here there is a quark that itself is a spin 1/2 particle, and so on. All this information is what I call trivial Lorentz and Dirac structures, which are things that we know how to handle. They're just mechanical. Somehow there is nothing conceptually complicated in that. They're important because they tell us what these particles are, what their identity is, that the Higgs boson is a scalar, the gluon is a spin 1 particle, and so on and so forth. So we have to carry this. But I'm going to strip all this information because this is trivial, it's easy, we know how to do that. And what remains, if you strip everything out of this, is what we call a scalar Feynman integral, which is something that usually we represent like this, as a graph. And since we have a particle that goes around this loop and its momentum is not constrained, because if you try to apply momentum conservation at every vertex, you will see that, of course, the momentum, there is one momentum that is not constrained, that is the one that runs around here. What I actually have to do is that I have to parameterize it somehow. This is a possible choice. I gave it a name K. This is the loop momentum that runs around here. And these are the numberings P1, P2, P3, P4 of the particles around here. And then out of this, I get an integral that looks like this, right? And these are the objects that we want to compute. Now, when you try to do this decomposition that I told you before, right? So to remove, to strip all these Lorentz structures and some spinors and so on and so forth, what you get at the end of the day is really something like this. You get like a combination of a lot of integrals here, which are the scalar integrals that I showed you now, and then a lot of stuff which is practically rational functions. So stuff that is kind of easy, that comes from all this decomposition that we did. This type of decomposition is actually very important because it actually allows us to start seeing the analytic structure of the amplitude. And it also is important to realize that the analytic structure of the amplitude actually has to reflect basic physical principles of quantum field theory. It's not random, okay? And this is actually one thing that helps us a lot in understanding how to do these calculations and how to simplify these calculations. In particular, the integrals are the difficult part, if you want. And when you do an integral, you typically get a complicated function out of it. For example, you get a logarithm, or you get a multiple point logarithm, or you get strange numbers like pi or zeta 3 or whatever. And these special functions and special numbers, they are objects that have a complicated analytic structure on the complex plane, though in particular have branch cuts, right? So places where they develop imaginary parts. And these branch cuts, together with the poles that come from the rational functions, are actually dictated, their position, they have to be dictated by physics. In particular, they are dictated by where the virtual particles that we saw here, these particles that run in the loop, they go on shell. So this is very important to realize, right? Because when one uses this actually can give you a lot of information a priori about this final structure of the scattering amplitude. And so what we actually try to do at the end of the day, typically, is that we have an amplitude, right? So we have an integrand, which means a sum of Feynman diagrams, right? Which like I did before, some Feynman diagrams gives you integrals. So in particular, it gives you the integrand, which is whatever we want to integrate over. Then this integrand, we want to decompose it into building blocks. And then we want to try to compute this building block somehow, and then to put together the result. And what typically happens when we do this is that the final result is actually much, much simpler than what we had to do in order to get there. So typically, these computations explode in your face, they become very ugly, and then you finally put everything together, a lot of structure cancels, and finally you get something that looks very simple. Okay, if you can call this simple, I don't know, depending again on your taste. And in a sense, what a lot of what people like me are trying to do today is actually try to understand how to get here in the fastest and best way possible, so that you avoid all the complexity of these steps, or as much as possible the complexity of these steps, to try to use physical information and mathematics, because there is some mathematics in these functions, to somehow translate physics into mathematics, right? And somehow get immediately to this result. So there are interesting open questions, right, about this, and in particular, the way we think about this is really, can we say a priori what are the numbers and what are the functions that appear in the final result? And if we can say that, how does physics, through the type of properties that I was describing before, how does it constrain the mathematical properties of the results? So which type of functions really appear, or which ones don't, or in which combination? And also, what is the shortest path to get to the simplest form of the result? And now, one way to understand these questions, as I was trying to say before, is exploiting this geometrical picture that I'm finally getting to describe, I hope. So again, we said we start from an amplitude. For example, now I'm writing an amplitude for the scattering of 4 gluons, and now even at 3 loops, right? So things become very nasty. So it is indeed a sum of Feynman diagrams. So I can write down all the Feynman diagrams. I get a lot of them, thousands and thousands. In this particular case, 50,000 Feynman diagrams. I also get out of this decomposition that I was telling you before, something like 10 million different integrals. So it's really a disaster, right? It's very complicated. Now, interestingly, out of all these millions of integrals, we don't really need to look exactly at what they look like, but there are, of course, propagators. There could be numerators that come from all this algebra that we do, and we integrate on all the loops, depending on how many loops we have, in this case, 3. K are the loop momenta, P are the external momenta, but again, it doesn't matter really what these things look like. One first thing that you should notice here is that because of what I was saying before, at the very beginning, some 10 minutes ago maybe, that these pieces individually are divergent, are complicated, they are unphysical, we need to somehow regulate these integrals, otherwise we would get a lot of infinities everywhere. And we do this computing these integrals in d dimensions, so we don't compute them in 4 dimensions. This is called dimensional regularization. This is a very important thing because it's a very powerful scheme that on one hand makes calculations very somehow streamlined, but on the other hand, it introduces some complexity, which is this fact that we don't work in 4 dimensions anymore. We are doing something unphysical. We will see that things become simpler when we go again close to 4 dimensions, but we have to do it somehow in the right way. Nevertheless, we will use these d dimensions for now because, as you will see, they really streamline a lot what we can do. All the integrals are convergent and well-defined in d dimensions, and that's why we compute integrals in this way. Now, the first important thing, exactly because we work in d dimensions, is that these integrals, there are millions of them, as we said, 10 to the 7 I wrote here in this particular calculation. They are not independent. There are a lot of relations among these integrals. And these relations, the most important ones, are called integration by parts identities, IBPs, right? So these IBPs will come over and over again. These are really integration by parts in the standard way. So I take a derivative of the integrand, and now since I'm in d dimensions and the integral is convergent, this derivative would give me the value of the integrand at the boundary, which is at infinity, which must be 0, because otherwise the integral would not be convergent. And this is the reason why dimensional regularization is so powerful, for example, because I can do integration by parts identities without having to think. So there are a lot of identities which I obtain performing these derivatives explicitly and writing down an identity equal to 0. And this connects a lot of integrals of the same type, one to the other. When I solve these identities, for example, for this case that we were looking at now, we started from 10 million integrals, I said, and we go down to actually 500, right? Which is pretty impressive because you start really from a number of integrals that you wouldn't even know how to compute to a very small number, well, kind of small, which is 500. Now, these integrals, you have to think about them really as a basis in a vector space, right? Really like in linear algebra. So you have a vector space, which is the space of all the Feynman integrals, and the master integrals, they give you a basis in this space. And as in a linear algebra, you can change basis, for example, and make your problem more or less complicated, depending on what you do. It has also been proven that, for example, this basis is always finite. So this is really a finite dimensional vector space. I also want to show you a little bit how we think about these integrals, okay? Because we usually organize them in what we call a tree, right? So imagine that you're computing something that is, for example, the scattering of 4 gluons or 3 gluons and a Higgs. Then you have, at the basis of this calculation, if you strip again all the polarizations and all this type of structure that I was telling you before, you have a graph that looks like a box, right? Because you have 4 particles. Now, of course, there are numerators on this box because there are all the numerators, as I was telling you before, that come from all the polarizations and everything. And so what you do when you start simplifying the numerators against the denominators is that typically you produce simpler integrals. You don't have only boxes, but you have triangles, for example. And we say in jargon that we pinch a propagator in all possible ways. We remove it from some numerator. We get triangles. We can keep on pinching and we can get, for example, bubbles, or we can get tadpoles. And this set of all these integrals is what we call an integral family or a family tree or whatever, depending on how people like to call it. So this is to say that when we think about an integral, we don't think only about an integral, but we think about the whole family of integrals that are attached to this problem in all possible ways, as you can remove propagators, right, in here. So if you have a box, you're also having triangles, bubbles, and tadpoles at the same time. Now, there is one important thing that I want to say, not prove here, but just state, is that if you have integrals at one loop, like these ones, it always happens that for each one of these new graphs that you can write, there is always at most one master integral, one new integral that you have to compute, no more than that, not 2. There could be 0. It could be that one of these graphs is not relevant, or in a sense, it can be shown to be equivalent to something simpler, for example, through an integration by part identity again. But in general, there will be at most 1. Yeah. This is important, as we will see in a second, because when you go to 2 loops, and this is one of the simplest things that you can imagine to do at 2 loops, this is a generalization of a bubble. And it's a 2-loop bubble that is called the sunrise integral. This is not true anymore. So it can be that in a single graph, like this one here, a 2-loop, you actually need 2 master integrals to represent everything that there is in here. Again, if you try to parameterize this thing with an internal momentum and 2-loop momenta, you get an integral of this type, right? Where you have K1, which is the loop that runs here, K2, that is the loop that runs here. And by momentum conservation, you have K1 minus K2 minus P that runs here. This other integral here that looks a little bit funny with this dot, this is also a notation that we use to indicate that one of these propagators has been squared. Yeah, so this is just a new integral in the same family that is also needed. This is an element of the basis. You just try to find your basis, to use all the identities that you find, and you see that one integral is not enough. You need 2, right? That's just a fact of life in this case. Again, here I'm assuming now that these propagators have a mass, right? But again, also in this case, if the mass is always the same, you can remove one propagator in all possible ways, but you always end up with the same thing. That is what is called the double tadpole. So the family in this case would be just these 3 integrals, right? So you see, in this case, the family is even simpler than the 1-loop box. It has fewer integrals, just 3. But there is this crucial difference that there is a particular graph which itself has, if you want, 2 integrals that are required to map all the integrals in this graph. So let's remember about this distinction. At 1 loop, there is always 1 integral. At 2 loops, there can be 2 or 3 or 4 or 9 or whatever. Now, why is this important? Well, this is important because thanks to integration of parts identities, the simplest way to actually compute these master integrals, once we have found them, once we have our basis, for example, this is our basis of integrals for this problem, the simplest way to compute it turns out to be deriving differential equations for them and solving the differential equations, not trying to do the integral, because the integral is extremely complicated to do in general. And this comes from the fact that you can take a derivative with respect to any of the variables that the integral depends on, and you're going to get integrals always of the same type. So you can take one of the masters in particular, for example, this guy here, you can differentiate it and you will get again integrals that belong to the same graph. And you can then reduce these integrals to masters, and so you get again the same type of master integrals. So what you get is actually that if you put all your integrals into a vector, you can differentiate it and you get a system of differential equations with a big matrix here that couples all these integrals to each other, right? And now it turns out that this matrix is always made only of rational functions. This is because of how IDPs work, right? It's kind of obvious or trivial. Good. Now, this matrix is true that couples all the integrals to each other, but it not really couples them in a complete random way, because since some integrals are more complicated than others, or if you want, some integrals are contained into other integrals, this matrix has a sort of block diagonal form. So there are like more complicated integrals that have the other integrals in their inhomogeneous terms, but then there is a big zero here. Yeah. If you look explicitly at the problem that we did before, you could have like some blocks here that couple two integrals in the same graph. For example, here, for this graph, there would be a 2x2 coupled block here because there are two masters that couple to each other here. And then there would be somewhere in the back a small 1x1 block of an integral that is simpler and easier, right? So in order to solve the differential equations for these guys, I need to know this guy, but not vice versa, of course, because this guy is simpler. So I can solve this guy and then consider the other ones. Now, this pattern is true. Everything we said until now is completely true in general D dimensions. We always use the fact that we are working in D dimensions. Now, what I would like to do is actually see and give you an idea of how things simplify when we go to 4 dimensions, can simplify, and where this geometrical picture comes from. So let's zoom on one of these blocks. For example, the 2x2 block that couples these two guys here. So what happens is that depending on the type of the graph, this block might become simpler when I go close to 4 dimensions, right? Imagine that I write 4 as d as 4 minus 2 epsilon. Epsilon is a very small positive parameter, and I expand in epsilon, which is what we typically do. Now, if I take a case like the sunrise that I wrote before, but I make these two propagators massless, these are the dotted propagators here, it means that they don't have a mass anymore, but I still have two masters here, two master integrals. What actually happens is that close to 4 dimensions, the matrix takes this form. So there is a 0 that pops up here in this corner, which tells me that actually close to d equal 4, I can solve the equations, even if they are coupled, they actually decouple. I can solve the first one, then put the result in the second one and solve the second one, trivially. Now remember that these quantities here, they were rational functions, as I told you before. So what practically happens out of this, stretching a little bit the argument, because I'm sweeping some details under the rug, but stretching a little bit the argument, what happens here is that you only have to do, at the end of the day, integrals over rational functions. Order by order in epsilon, you keep on integrating over and over this type of matrices, and you just integrate the first one, you put it in the second one, you integrate again, and so on and so forth. So what you get are integrals over rational functions. Now, integrals over rational functions are trivial. If you have a rational function, you integrate it, you get another rational function, unless the rational function has a single pole. If the rational function has a single pole, so it has a singularity of this type, then you get a log. And the reason why you get a log is because a single pole is something that in the complex plane has a residue, which is different from 0. So if you go around it, you get something different from 0. And so it tells you that the primitive of this object is actually a function that is multivalued. If you keep on generalizing this thing over and over, so integrating rational functions, you get actually what are called multiple point logarithms. You keep on integrating over single poles and you get generalizations of this log. Now, where is the geometry here? Well, here the geometrical picture is trivial at this point, and it also doesn't add too much information at this particular point of the argument, because the geometry is in the fact that integrals of this type are called integrals defined on the Riemann sphere. Why? Because the Riemann sphere is just a complex plane that we looked at before, with the addition of the point at infinity. And there is a theorem, a mathematical theorem, that tells us that the only single-valued functions that exist on the Riemann sphere are rational functions. And so the only integrals that I can consider, if I want to consider well-defined integrals on this sphere, are these logs or these polylogs. There is nothing else, okay? So this is where the geometrical picture comes in, if you want, a posteriori in this type of construction at this point. Now, if we stop at this, actually understanding this geometrical picture, understanding the structure of these differential forms of logarithms that are these d-logs that I wrote here, these logarithms that we have here, we don't have even to call them d-logs, was extremely important because it allowed us to compute so many amplitudes for collider physics. In particular, the most important ones, I would say, for some of the most important ones, are the ones that have to do with the production of massless particles. For example, gluons or quarks, massless jets, which have been computed up to 3 loops, 2 to 2, 3 loops, 2 to 3, 2 loops, and 2 to 1 in a sense. 4 loops, these are called form factors. And they are being very important to model QCD dynamics in very high precision. I think one of the most impressive results was obtained indeed by René himself, who used some of these amplitudes in order to do very precise calculations for the production, for observables that have to do with the production of 3 jets, so 3 colored particles in the final state. But now, so does this help us at all? So why is this important? And how general is this picture? Well, in the last 5 minutes, hopefully, I want to just give you an idea of what happens in more complicated cases and why this general picture can be useful, this geometrical picture can be useful. Let's go back to the same example that we had before, but now let's make all these propagators massive. They are not too massless anymore. Well, it turns out that in this case, if you take this limit, unfortunately, the matrix does not decouple. There is no zero here. So things remain coupled and complicated. So it means that there is an intrinsic higher order equation of second order here. This is what the equation looks like, and nobody cares what it really looks like. You can forget about that. I just want to say that this type of graphs, they are not irrelevant. They appear in some of the first and simplest calculations that you can imagine to do at 2 loops in quantum field theory. For example, the corrections to the electron propagator in QED that were attempted, this calculation, in 1962 by Sabri. Indeed, inside this type of graphs, you find, if you pinch propagators, as I showed you before, if you pinch the 2 massless ones, the 2 photons, you find exactly the sunrise graph. And if you pinch these 2 massive 1 and 5, you find indeed the other massless sunrise that we discussed before. So you find something that is polylogarithmic, that is what we looked at before, but also you find this new guy. And now, what is this new guy? Well, this differential equation, well, it's complicated, right? So you have to hope that somehow you know how to solve it. In this case, you can actually solve it, and you can show that it is connected to an elliptic curve. But what is interesting to notice is that this connection to an elliptic curve can actually be obtained directly from physics, again, namely from unitarity, namely from studying what happens if the internal particles, again, here go on shell. Again, this is a little bit technical, so I don't want to say anything about this, except that if you put these particles on shell, you compute a quantity which is very simple to compute. It's called the maximal cut, technically, but it has to do somehow with the cross-section, the probability to produce these 3 particles for real. And this thing is actually a building block of the final graph because of unitarity, as I was saying before. And if you do this calculation, you indeed find a complicated square root. You find a strange integral, which is much different than the logarithmic integrals that we were looking at before. There is no rational function here. There is a complicated algebraic function of a complicated polynomial of degree 4, right? And now, so what is the difference? Why is this so much more complicated? Well, and here's where the geometry comes, right? Because if you have a polynomial of degree 4, it's not true anymore that your function is well defined on a sphere, as we said before. it turns out actually that the place where a polynomial of degree 4, a square root of a polynomial of degree 4 is well defined is not a sphere, but is a torus. This is what is called the Riemann surface associated to this square root. The way to see this is realizing that indeed, because of this structure, you have two branch cuts, and these two branch cuts, they come in two pairs because of the two possible solutions. And when you glue these two surfaces together, then you get really something like a torus. Again, this is a little bit technical. If you want, I can explain this better afterwards. But the important thing is that there is a geometrical picture that here generalizes, and it goes from a sphere to a torus. And so what changes really? So we looked at the sphere before, right? And we said here, there are only rational functions on the sphere. And in particular, if there is a singularity which corresponds to a single pole here, when I integrate over the singularity, which is this little star here on the complex plane, I get a logarithm. And that's everything that there is, right? There is nothing else. If I have a torus, well, now having understood that there is a geometrical picture behind, things are actually much easier to generalize starting from here, because I can have the same thing, right? I can have a pole somewhere that gives me what are called integrals of the third kind. But I can also get new objects which are not there on the sphere, which are different ways how I can move on the torus, which are so-called forms of the first kind and second kind. Technicalities, I mean, these are no poles or double poles, but this is all technical, it's not so important. What is important is that the geometrical picture is more interesting, but it's clear. There is no question about what is going to happen. And thanks to this, one can generalize the type of calculational techniques that we use on the sphere and that have been so powerful to do these calculations, including, say, three-jet production that I talked about before, go beyond them on the sphere. And I just want to make a super simple example, actually two super simple examples, and then close it here, which are, where do these things appear? I showed you the two-loop electron propagator. The same things appear also at three loops. Say when you go to the three-loop electron propagator, you have graphs of this type, which can have the same type of structure inside, a cut that goes through 1, 2, 3 massive particles, which again can be related to the sunrise. And the fact that you understand, I mean, it's not so important what this looks like, but the fact you understand the geometry, you can derive these differential equations, you can solve them very nicely, and you can get analytic results and actually also numerical results for these quantities everywhere on the phase space. And things can become even more complicated because say that you consider now the photon propagator to three loops instead of the electron propagator, then actually here you can have graphs where you go through cutting 4 massive particles, not 3. And these correspond to a generalization of the sunrise to 3 loops, where the geometry is not elliptic anymore, but is a multidimensional generalization, is the first example of a Calabi-Yau geometry that is called the K-tree geometry. And also here you can use the same techniques, and once you have this understanding, you can actually compute the quantity analytically and numerically, which I think is actually very nice. And finally, I mean, I want to close just saying that this thing generalizes to many other problems. There are elliptic problems in, say, real scattering amplitudes, 2-2 problems at the LHC. There are multi-dimensional generalizations, so Calabi-Yau geometries in many problems at multi-loops. And there are even generalization with more holes, like you say, higher genus, even already at 2 loops. And so trying to having understood now how this thing goes, we hope, of course, to be able to extend this to more complicated geometries. An example also where Calabi-Yaus were important most recently was observed also in the modeling of gravitational waves, that the same type of quantities appear when doing post-Minkowskian expansion to the 5th order, so for loop calculation. And so this brings me to my conclusion. I want to close this. I've said a lot of things. So I tried to convince you, I hope, that amplitudes are fundamental building blocks in QFT. I also tried to tell you that the complexity of the calculation often hides simplicity. And now we start having like some way to see where part of the structure at least comes from, which is connected to the way differential geometry, and geometry in particular, in general, actually tells us what can happen, what types of functions can appear. And we are able now also to use all these mathematics that have been developed in the last 10 years, at least exported to physics in the last 10 years, to start doing some real calculations that have impact both for collider physics, hopefully, but also gravitational waves. And so I think this is actually very exciting, and I hope that I could at least convey you a little bit of what is behind this. I realize it's a little bit technical, well, maybe very technical, but maybe you try to, you understood something out of what I said. And with this, I thank you for your attention. Sorry for being a little bit late. Yeah.